Hello friends, welcome to a new video in data science and machine learning techniques. Today we are going to see the dimensionality reduction techniques which are used in the supervised machine learning. Now this is acting as a support to the other machine learning algorithms. So we are going to see how exactly these algorithms will affect your techniques or your already used supervised machine learning techniques, so that we can have improved accuracy and more accurate classifiers can be generated with this. The concept is called as dimensionality reductions. Dimensionality reduction is or dimension reduction is the process of reducing the number of random variables under consideration by obtaining a set of principal variables. It can be divided into feature selection or feature extraction. The feature selection approaches to try to find out the subset of the original variables, also called as feature or the attributes. Features projection or feature extraction transform the data in the high dimensional space to a space of fewer dimensions. Okay, so dimensions we are going to change. We are going to change the features. We are going to identify the top features which will affect the output of your algorithm. Okay, so based on that, this feature selection technique will give you the principal components which will affect your output and will generate more accuracy than the other classifiers. What's the meaning of large dimensions? Large number of features in the data set is one of the factors that affect both the training time as well as the accuracy of machine learning models. You have different options to deal with the huge number of features in the data set. Like, try to train model on original number of features which take days, weeks. If number of features are too high, now what we'll do, we'll reduce the number of variables by merging the correlated variables. Now extract the most important features from the data set that are responsible for maximum variance in the output. Different statistical techniques are used in this purpose, called as linear discriminant analysis, factor analysis, and principal component analysis. So we are going to see two techniques here in practical based approach, that's what we call as PCA and the LDA, by which we can get high dimensionality reductions and we can generate better output with the low dimensions also. First, we'll start with the PCA. PCA stands for principal component analysis. Is a statistical technique to convert the high dimensional data into low dimensional data by selecting the most important features that captures maximum information about the data set. The features are selected on the basis of variance that they cause in the output. Okay, the features are selected on the basis of variance that they cause in the output. The feature that causes highest variance is the first principal component. Variance means impact. Okay, the feature which causes highest variance in the output is called as first principal component. The feature that is responsible for second highest variance is called as second principal component, and so on. It's important to mention that principal components do not have any correlation with each other. Just consider we are having two input features like age and the date of birth. Make sure that age and date of birth are the variables which are correlated to each other. If such kind of things are there, okay, so a principal component analysis will not work better. Now, what are the advantages of this? The training time of the algorithm reduces significantly with less number of features. Okay, so whatever number of features, if you are having 50 features, out of that only 10 features you are taking as input, then obviously the algorithm's training time will be reduced drastically, and we are going to train algorithm with least number of time. So maybe when huge amount of data in terms of rows is present, okay, it's not possible to reduce that data, so we can reduce the dimensions, that is the number of features or the number of columns. It's not always possible to analyze the data in high dimensions. For instance, if there are 100 features in the data set, total number of scatter plots required to visualize the data can be 4950. Practically this is not possible to analyze the data in this way. That's why reduction in the dimension is expected. So PCA can do this one, but there are some, okay, so let's go for the normalization of the features. So one important things to mention here is that data should be normalized before applying to PCA. Means either it should be min max scaled or it should be standard scale, that is it should be applied with feature scaling or can be applied with the min max scaling there. Okay, so for instance, if a feature has expressed in units of kilograms, light years or millions, the variance scale is huge in the training data. So as we have discussed already, if magnitude is affecting the output, it means that if one feature is having some high magnitude, one is having some low magnitude. Okay, so the high magnitude data will have a highest impact in the output, but in case of PCA, for selecting the proper features for principal components, every feature must have similar thing, similar range, similar impact on the output. So to do this one, it is expected that your variance, if you want to keep this identify the perfect variance, all of their scale should be same. Okay, so if PCA is applied to such data where variance, too much different kind of scales are available in the data set, the resulted loadings for features will with high variance will also be large. Hence, principal components will be biased towards the features with high variance leading to the false results. Finally, the last point to remember before we start coding is PCA is a statistical technique and can only be applied to the numerical data. So, therefore, categorical features are required to be converted into numerical features before PCA can be applied. So, either we can use one hot encoding technique or the label encoding technique to convert these features, the categorical feature or the string data, in the form of the numerical data. So, that is what the prerequisites are there for the PCA. So, let us see how reduction in the dimension, reduction in the features can be achieved with the help of a PCA. For this particular technique, I have taken one interesting data set here, one of the most popularly used data set around different kind of algorithms is the Wisconsin's breast cancer analysis. The University of Wisconsin has donated this data set to UCI machine learning repository. You can download from there. You can see the link archive.ics.uci.edu. Here this breast cancer analysis data set is available, or you can download it from the MITU Skillologies data repository also. What's the meaning of the data set? That we'll talk first, and then we'll go for using this data. This is my data set whose file name is WISC_BC_data. You can see it on top. Fine. Now this data set is created from the different patients who are having cancer in their body. Now the cancer tumor has detected in their body, and these are the tumor dimensions created. So these are the tumor dimensions: radius mean, texture mean, perimeter mean. Check it out. These all are the tumor dimensions. Total 30 features are there, 30 dimensions are there. See, till AF. Okay, lot many dimensions are present. So based on these dimensions, it is identified that whether the diagnosis of that tumor is M or B. What's the meaning of M? M stands for malignant. Malignant. It means that the cancer is detected here in this particular body. Okay, in these tumors. And B means benign. Benign is healthy. Means the tumor is detected, but this is not cancerous. These are cancerous. These are not cancerous. So I am going to create a classification system. By all these 30 features, we are going to find the diagnosis of it, whether the cancer is the tumor is cancerous or not cancerous. You can see the combination is possible there. So it's coming under the classification category, whether the tumor is cancerous or not cancerous. So this is how I'm going to do the operation of this particular data, and let's see how PCA can be effectively applied to this kind of the algorithms over here. Okay, so let's go for that. Let's read this file. First of all, I'm opening the pandas, reading the importing pandas, read the file and check out the shape. This is important statement here. Now in this particular file, we are having 569 rows and 32 columns are present. How many? 32 columns are there. If you see these column names here, okay, these are the 32 columns there. It means that now we are going to create your algorithm based on these 32 columns. Now if 32 columns are used in this data, so it will take some time to train it, but if you consider number of rows can't be reduced, because all that carries the information common to all the particular data sets. Okay, so that's why columns are not possible to reduce, so we can reduce the number of features. Now out of all, top n number of features will use to train our algorithm here. Now how to decide that, how to use it? So see the columns. Now from this data set, we know that this is the output variable diagnosis and remaining are the inputs, but this is also not input. Make sure ID, serial number, roll numbers, they are not considered in the generation of model, because we know that they will not have any impact in the output. That's why ID I am going to delete. ID and diagnosis, these two are not the input variables, remaining are present. So out of 32 which we have seen here, out of 32, 30 features are used, 2 features I am dropping, ID and diagnosis. So ID and diagnosis I am dropping, and remaining 30 features I am putting into variable X. Fine. And output variable is your diagnosis, which I am storing inside the output variable Y. So X is input, which contains 30 features. Check it out. 569 rows and 30 columns are there, and Y contains one output variable, which is diagnosis. And if you see how many values are there in Y, so check it out, B and M. Okay, only two classes. Benign, B stands for healthy, benign, and M stands for malignant, which is cancerous. Okay, so let's build a model and we'll try to find the classification systems and its accuracy. So let's split our data. Let's apply our algorithm like random forest classifier. I'm randomly using a data set or algorithm here. You can choose any other also. So I'm converting data in trend test format 2575, and then I'm reading the random forest classifier. Okay, and for random forest classifier, number of estimators I have given 100, number of trees are 100 here. Classifier is built. So with the help of 100 trees, I have created this particular classifier. So let's fit our data, X train, Y train. Okay, let's see how many entries are present in this. So length of X train, out of 569, 426 entries are there for training data on which you are going to build your model. Okay, so model is built, and now for remaining entries, remaining almost 120 more than that entries, we are going to predict it. Fine. So same operations we are doing here. So let's read the confusion matrix and accuracy score. So right, then accuracy score, check this. Yeah, I got 96.50% accuracy for this data. Okay, random forest classifier, I'm going to have the 96.50% accuracy on this data if you apply the random forest classifier then. Okay, this is the generalized case that I'll be using over here. Make sure that I have not used the random state over here. Let's see the random state also. So it will, okay, let's go for that. Yeah, random state I'm keeping 0. So a bit accuracy changes are achieved here. 97.20% accuracy is present for basic random forest classifier if you apply to the Wisconsin breast cancer analysis data set. So that's good, that's fine. But the problem here is that we are having 30 inputs given there. The 30 inputs are generating your results. Okay, 30 inputs are there. So can I reduce this number of features to some 10, 15 or 20 like that, so that algorithm training time will be reduced? Here I have only 569 rows. That's why random forest classifier is not taking much time. But if the number of rows are in lakhs, 10 lakhs or crores, in that case the algorithm will take some time for the predictions. So in that case we'll have a problem. So you can see here 4 misclassifications are there in case of this particular data, or 30 rows are there. And if I'm going to check from training data, I'm taking 198 number of rows, and I'm going to find whether it's B or M, because 30 inputs are there. So out of 30, it's very difficult to give the 30 inputs. I'm taking row number 98 in the new, and I'm predicting for that new what class is that, whether it is M, that is malignant, or benign M. So this is what my basic operations of machine learning completed till this. Now onwards, now we are going to check how PCA can be applied, how the reduction in the dimension can be achieved with this. So as I mentioned in the slides also, PCA requires the scaling of the data compulsorily, that is normalization is compulsorily required. So because variance, all the output or input variables should have the similar impact in the output variable. Finally, you can check it out, their ranges are different. This is in hundreds, see this. This is in almost thousands also, and these are in 10s, 20s, 30s, like that's why their ranges are different. This is in 0.0 something here also. So it means that it has this different scaling. So I require and compulsory to have the scaling over here. So let's import the min max scaler. I'll create the object of this scaler over here and transform my X data into the X scale data. Okay, now scaling is completed. Now we'll come with the PCA. Now PCA, first of all, let's analyze the PCA first, try to understand how PCA actually perform the operations, and then we are going to see how it should be applied. Okay, so let's see this. First of all, I'll from sklearn.decomposition, I'll import the PCA. Okay, so PCA is a class present inside a decomposition package of sklearn. Okay, let's import it. Now PCA object I am creating over here. PCA is equal to PCA, nothing I have passed over here. It actually contains the number of components to take. And now once the object is created, I am using fit underscore transform to transform my scale data into PCA format data. Okay, so high dimension data to low dimension, but remember here dimension I have not changed. First of all, we'll focus on it. See, so transformed, and now once it is transformed, inside this PCA there is a special variable created called as explained variance ratio. This explained variance ratio stores the variance, that is impact of every individual variable on the output. That is what we call as explained variance ratio. So this variance ratio for all the 30 variables is stored inside the variance in the sorted format. In this sorted format, remember, data is sorted with highest impact towards the lowest impact. So 30 different ratios are stored inside it. Now these 30 ratios I am going to show in the form of a graph, in a bar chart. How to see? So on X side I will show the number of principal components that will start from 0 to 30, sorry 1 to 30 here, and on Y side I will print the variance in terms of percentages, or if I multiply this number by 100 it will show in the percentages. And PLT.bar, X side I have the principal components, and Y side I am having the variance of that particular feature. So let's check it out. What happened? Okay, sorry, PLT, I need to import PLT first, so it's not defined there. Import matplotlib dot pyplot as PLT. Okay, so let's write this. Okay, see, okay, so these are the 30 features and this is your variance. Okay, on Y side I'm showing the variance. So first component is having almost more than 50% variance present there. Second component somewhat less than that. Next, like if I print this variance on this screen, so you can check it out, it will be shown the percentages. See, here the variances, variance of first component, principal component, second, third, fourth, fifth, like so this is 53 affecting the output, 53%, this is 17%, this is 7%, this is 6%, this is 4%, this is 3%, this is 1.58%, and go on. And then as you go ahead, these variances are decreasing at high extent. This is 5.96 in 10 raised to minus 4. See, so you just can check it out till 15. Variance is good, not exactly actually good, but it is above 1 to 2%. But after 15 and from almost 23 onwards, there is no impact of these particular features in the output. Fine. So impact is not there. Then why to use these particular features in the output? So we'll use some n principal components while using it over there. Done. So this is what we call as the variance, and the data is transformed in the form of the PCA, that is x underscore PCA. Okay, principal components are identified, their variance I am showing over here. Okay, so variance is shown. This is the impact of the respective features in sorted fashion, it's mentioned over here. Okay, that's done. Fine. Now this PCA transform data, so I applied from original data to scale to PCA. Okay, so I got top 30 features over there with principal component and impact of it. And after that, I am going to split this data again, which is PCA transform data, and train and find the accuracy score of it. Now check it. The overall accuracy after transforming to PCA, I am going to have it 91.60% only. Okay. Now don't consider that, because all 30 features in PCA format, high dimension low dimension format I am using. Now I am going to use the data with top n number of components only. Okay, so how to do this one? So what I'll do, I'll add one more cell here. Okay, so let's create this PCA here. So the number of components. Now I'm going to create the object of PCA again, but top n number of components I'll be using over there. So here I'll make use of it as 1. Okay, so only one feature out of all I'll take. Okay, so let's check it out. So what I'll do, check this. So PCA object I'm creating again, and that PCA I'm using fit transform to x scale data and generate x PCA again. But how many number of features I am giving? Only one feature, or only one column and one principal component over there. If I see the x underscore PCA shape, see 569 rows are correct, but only one feature which is having the highest impact in the output is chosen. That is called as first principal component. which contain the highest impact in the output is taken inside the consideration. So only one column is there. Out of 30 column, only one column is chosen which is having the highest variance for the output. Fine. So using single principal component, I have chosen this PCA, and after that I am going to apply this single component PCA to my train test. So X train, X test, Y train, Y test, train test split, X PCA, random state 0, and then let's check the shape. Okay, so that's done. We have splitted the data. Fine. And now splitted data we are going to train it. So our tasks are completed. We applied the PCA, we have chosen one principal component which is having highest impact in the output, and after that we have done the train test split, and then we are going to fit this data, PCA transform data and train test splitted data, to the classifier dot fit. Okay, and then classifier dot predict X test for remaining entries. I am predicting it Y pred, and now let's see what is the accuracy of this algorithm. 88%. Now we can check it out. On 30 we are having 97% accuracy, and on single feature I am having 88% accuracy. So I am having only difference of 9% there, and 29 features are reduced. Fine. So this is what the application of the principal components here. So only one component is generating the accurate classifier with 88% accuracy. Okay, so let's check with some others. I will make it 2. Okay, so 2 features, check it out. 2 features, now 95%. Top 2 features is giving 95% accuracy to me. 28 features are reduced, and only 2% reduction in the accuracy is there. Okay, that is 2 features is giving me. Let's check 3 features. Okay, again 93, somewhat it is reduced. Take it 4 features, 95%, and if I go to use 5 features, 95.80%. It's okay. We can achieve the accuracy. Only 2% difference is there, but the main problem here is that I am out of 30, 25 features are not taken in the considerations. Only top 5 features which is having highest impact in the output, only they are considered, and we are achieving significant accuracy out of it. That is the use of principal component analysis. That is reducing the dimensions, and reduced dimension features are applied to your data, and based on that we are generating more better results there. Okay, so this is how the PCA operations are performed. Okay, so let's continue with our program. It's what we have done, single dimension or multi-dimension features. Okay, so PCA class contains explain variance ratio, which returns the variance caused by each of the principal components in the output. Okay, that's we are going to use it. So you can try on different data sets, and significant accuracy also we can achieve from this particular technique of PCA. Next to that we are having one more technique called as LDA. So LDA, it's called as linear discriminant analysis. So normal discriminant analysis or discriminant function analysis is generalization of Fisher's linear discriminant, a method used in statistics, pattern recognition and machine learning to find a linear combination of features that characterizes or separates 2 or more classes of objects or events. The resulting combination may be used as a linear classifier or more commonly for dimensionality reduction before later classification systems. So how LDAs perform? It is bit not actually understandable if you don't know the statistics and its internal structure. I'll just read it out how LDAs perform. Compute the d-dimensional mean vector for different classes from data set, where d is the dimension of feature space. How many dimensions you have to give to feature space. Then compute in between class with in-class scatter matrices. Then compute the eigenvectors and corresponding eigenvalues for these scatter matrices. Then choose k eigenvectors corresponding to top k eigenvalues to form a transformation matrix of dimension d into k. Transform the d-dimensional feature space X to k-dimensional feature space XLDA via transformation matrix. Okay, these are the 5 features, 5 steps are taken there, but our prime task is to reduce your dimensions, but there is a difference in all. See PCA, what it does. PCA, component access that maximizes the variance. See which particular component is having high variance, that is identified by using PCA. Okay, in this way it maximizes the variance. The access are identified and based on their data is transformed. But in LDA maximizes the component access on class separations, which access is having highest possibility of class separation. That's what we are going to do over here this case. Okay, so it means that this is your class, okay, and this is your input. So So it means that LDA requires input and output both, and it identifies the axis which perfectly classify your data. Okay, so which axis will perfectly classify your data, that is identified by using LDA. It means that LDA algorithm, linear discriminant analysis algorithm, requires input and output both. Then only LDA will work perfectly. Okay, to reduce your dimensions. So let's go for using the LDAs now. How to apply the LDA? So here I applied the LDA. So from sklearn.discriminant analysis, so this package is used discriminant analysis. I am importing linear discriminant analysis. Actually, the class name is very big, linear discriminant analysis, just not like short as PCA. So what I have done, I have given an alternative name to it as LDA. So when I create the object, I want to use that LDA name is here. So this is alias I am providing over here. Fine. Now LDA is equal to LDA of number of components 1. So here I am choosing now single component to apply the LDA. Okay, so let's do that. So let's import LDA, create the object of LDA within one component, then split this data. Split your data, okay, in train test format, okay, or let's apply the LDA first and then we are going to do the operations. Okay, so split this data, scale data I am splitted, and now I am applying the transformation. So how to do this one? So I got this LDA dot fit transform. So LDA now I am going to apply on X train and Y train, X train and Y train separately. Okay, both parameters are required here because I want to find the axis which will perfectly classify the input and output. Okay, so that's done. And then test data also I have transformed on LDA. So same method which is used here, I am using fit with pattern is taken. Here I am only applying it on test data set. So I got the test data here applied. Okay, so I got LDA transform data, that is XLDA. Now let's fit it. So PCA transform data was PCA there, and now I'm using XLDA LDA transform data. So classifier dot fit XLDA comma Y train. So train data is taken as it is. After that classifier is fitted, I'm going to do the prediction on the remaining data, which is again transformed by the LDA, because on both input output test and train the LDA transformation is expected. Okay, so I got the predicted output out of it. Then accuracy underscore score is equal to Y test into Y pred into 100. So check it out, 97% original accuracy by using single component, all 30 components on random forest classifier, and now in LDA on PCA with 5 components I achieved the accuracy of 95.80%, and now LDA with one principal component, how much accuracy is? Yes, 95.80% with one principal component, one component in linear discriminant analysis, we have achieved 95.80% accuracy. If you see this one, X underscore LDA dot shape, see 426 and one column is present only. 146 is training data sets length is there, and 1 is the only component which is mapped. So one axis is perfectly classifying this particular data, and they are giving me 95.80% accuracy. It means that 29 features are reduced, only one feature is used over there in LDA. And same we are using PCA also by using 5 components. So 25 features are reduced in PCA. But the problem here is that it will take some time in LDA, because LDA needs input and output both, whereas PCA don't need these things. Okay, so LDA requires both, okay, transformation, and PCA don't require that. PCA only require the input data, scaled data, and then only it will use it. This is how LDA and PCA can be used to reduce the dimensions. The number of features required to build a classifier will be reduced drastically. Even on single feature also we can achieve good and proper accuracy out of it, so that the time required for training and time required for the prediction will also get reduced. So these techniques are used for the dimensionality reduction system. So you can apply that on any kind of before using any kind of classifier, or on any kind of the data that you will be using, either for classifier algorithms or for the regression algorithms. Just try on your system, try on different kind of data sets. Thank you. Thanks a lot.